process specifically dedicated to pathogens inactivation. Disinfection is a trade-off process, since achieving the goal of pathogens reduction means generating some environmental drawbacks, such as ecotoxicological effect for the aquatic ecosystem, disinfection byproducts formation being the majority unknown and many toxic, high energy requirements, especially in case of UV radiation. It is therefore important to properly design and control the process, to use the right amount of disinfectant, avoiding under or over dosages, assuring a proper balance among the different aspects characterizing this process. Thus, let's have an insight about disinfection reactor design, process modeling, and control. Historically, disinfection process has not been implemented in wastewater treatment plants, resulting in a negligible need for robust descriptive models for its design and control. About chemical disinfection, the most used reactor configuration is based on open-air chicane contact tanks, designed to approximate ideal plug flow reactors in order to assure the contact time required for a proper inactivation extent. In absence of specific reactors models and experimental validation tests, the design of chicane contact tanks can be empirically performed according to general rules on their geometric characteristics, aimed at reproducing as much as possible the ideal plug flow behavior. Disinfectant dosage, being the dosage of the reagent or the delivered UV intensity, has to be optimized in order to guarantee the required pathogen reduction, while minimizing drawbacks, meaning residual concentration of disinfectant, which implies an ecotoxicological impact and process cost. In the wastewater treatment field, this goal is challenged by the fluctuations in quality and flow rate of wastewater to be disinfected, which impacts on two fundamental operating parameters in determining process efficiency: the concentration of disinfectant and contact time. As a result, process efficiency can be significantly affected, leading to possible unexpected under or over dosages. In more details, wastewater quality impacts on decay kinetics of disinfectants, which can be described with a modified first-order kinetic. About inactivation models, one of the most widely adopted models is the OHM model. Better design criteria with respect to the empirical ones come from more detailed process modeling approaches, able to take into account wastewater quality and flow rate variability. Chronologically speaking, the first approach to disinfection modeling was the surface water treatment rule. It is based on the concept of disinfectant dose, assumed to be the primary factor determining disinfection efficiency, and conceived as the so-called CT product, defined as the product of disinfectant concentration and residence time in the contact tank, whose values are assumed with a very conservative approach. The assumption on the importance of the dose is the basis of most of the following modeling approaches to disinfection, which nevertheless maintain the conservative feature of a single objective approach, which looks for a high safety factor when considering pathogen inactivation, while neglecting the environmental and economic impact of unnecessary overdosage. The step forward in modeling the disinfection process is represented by the Integrated Disinfection Design Framework, IDDF, which led to a fundamental shift towards a site-specific modeling of continuous flow disinfection, which considered contact tank hydraulics, microbial inactivation kinetics, and disinfectant decay and byproduct formation. However, IDDF was developed for drinking water and considers disinfection as a stationary process with constant water quality and flow rate, which makes it very approximate for realistic wastewater applications. More recently, variability of process inputs and model uncertainty were included in wastewater disinfection modeling, adopting stochastic models or explicitly modeling temporal dynamics of the process over time. All modeling approaches listed so far are mechanistic, since they try to explicitly describe physical phenomena involved in disinfection. Statistical regression models represent an effective alternative whenever lack of knowledge can be compensated by directly capturing process behavior in data. An example is represented by the exploitation of artificial neural networks for modeling a wastewater ultraviolet disinfection, providing a support for process optimization and control. Usual approaches for UV radiation modeling are based on the detailed modeling of hydrodynamics and UV radiation intensity via computational fluid dynamics, coupled to lab studies of inactivation kinetics. This kind of approach provides accurate predictive performance, but it requires significantly high computational time, making it unfeasible for real-time process control. However, black box regression models based on artificial neural network enable an effective process control, even when a stringent microbiological discharge limit is required, as in case of wastewater reuse. The application of the model on a UV disinfection of a full-scale wastewater treatment plant permitted to estimate a 63% energy saving. In conclusion, the disinfection process is fundamental to assure a safety discharge and reuse of wastewater, providing an essential resource to the environment and agriculture, reducing the potential for conflicts among stakeholders in a climate change scenario. Anyway, further research efforts are required to achieve a full description of the process useful for its optimized management, leading to the minimization of environmental impacts and costs while maximizing the safety extent.